So in this video, I'm going to discuss HTTP fundamentals. And that involves things like just the basic request and response model and all the different components involved there. Then I'm going to go on to topics like caching, for example, and how a full stack application communicates. So to start with, let's discuss the characteristics. So we go up the TCP network communication stack here. The application layer, there's the standard HTTP and HTTPS. So that's quite common. We know what that is and what the TCP listeners are for that. The standard communication stack. So there's two varieties, unencrypted and encrypted. HTTP is a data transfer protocol at the application layer. That's what it does. It's based on a client-server request-response model. Send a request, get a response. So it's pretty basic, but it works quite well. There's several methods involved. The most popular are get and post. There's also delete and also put. So those are the four most important and most used. But there's also some others as well. And some of the services involved with HTTP involve caching, compression, and authentication services. So I'm going to start with the request response model and just kind of give an overview here. So as mentioned, it's a request and response kind of basic transaction communication between client and server. You've got a GET request, and that really amounts to retrieving data from a web server. And it's read-only. It's cacheable. All requests are cacheable. The data type is ASCII, and that's just basic text, although that changes with version. The URL length is a maximum of 2,048 characters, and it's sending a request to the server, so no actual data. It really is just some headers. So it's pretty lightweight. Like I said, there's no data. So that's basically kind of an overview of a GET request. And the POST request, that's a create or an update resource on a web server. So you send a POST for that purpose. It's not cacheable. So you send the request body to the server and the response body to the client. There's actually any data type is supported, and data length is unlimited. So basically the POST request, and this is a request, so you have to realize it's being sent from the client. And it's things like form data. So really what you're doing is replacing something there. It's not cacheable, and it's sending a request body to the server and a response body to the client is optional. So sometimes there's a response to the client, sometimes there isn't. And finally there's a delete request. So that's deleting a resource on the web server, pretty straightforward. It's not cacheable either. So the request body is to the server is optional, so you don't have to send data. And the response body is optional as well. Then I've got some HTTP response codes. This is quite important for troubleshooting, really. So the 100 series, and that's really just informational. Anytime you get 100, 101, 102, it's just informational codes from the server. And then you've got the 200 series, and that's basically whether something worked or not. Usually just amounts to just a 200 OK. Then you've got the redirects, and they're the 300s, like 304 and not modified is quite popular. And it also amounts to just a lot of redirect issues. Then you've got client errors, and that's 401 authorized is a quite popular one. And that's just any time you have any errors. Often it has to do with security issues. You'll get 400 errors where the client can't connect. And finally, there's the 500 series response code, and that's basically server errors. And you get things like 503 service unavailable. Maybe there's maintenance being done on the server. So basically, the troubleshooting aspects, usually 300, 400, 500, are really something you concern yourself with when you're doing maybe troubleshooting. And there's some additional HTTP methods like head, and that just refers to header. And that's a GET request with no response body return. So you're just asking for the headers to be sent. And then the patch is just a partial modification of a resource. Then you have options, and that specifies communication parameters with TCP, for example. And then a connect is for initiating a tunnel with a peer. And trace is to do a message loopback test to debug the forwarding path. The HTTP request components, looking a little further into HTTP request, It's really comprised of a request line, headers, and the body is optional, like I mentioned before, with a post it's there. So our request line starts with an HTTP method, whether it's a get, a post, a put, or a delete. So you start with a method, and then you also add a relative URL resource path, and then a protocol version. And then the headers themselves, and they're just a variety of headers, request headers. You've got things like host, for example, that's the server. Then a connection would be referred to whether using keep alive or not. And then accept language, whether it's US or French or something else. Accept means just the kind of format you can accept, whether it's text, HTML, things like that. Then cache control, whether you're using cache control or not. Then user agent would be, whether it's Chrome or Mozilla or something. And then finally authorization, the authorization header. And those are just some of the common ones, really. Then the body is optional. HTML form payload is probably the best example, and informational messages. So I've got some examples here, right at the bottom here. Got get here and courses web. So when it's a relative, a relative doesn't include the HTTPS. It just includes just the path that you add to the host name, basically, and you get the absolute path, but this is just the relative path, not including the domain name. Then HTTP 1.1 is the version, so that's the top level. So it's method, path, and version. That's kind of standard. Then host, udemy.com, that's the server. Connection is keep alive, that's for connection reuse. And then the language, the format type of text, or what's supported, cache control, and user agents. This is a post. This is sending some form data. So it's a post. And there's the path, form user data, and the version. And basically that would be content type would be application and JSON encoding. And then the content length would be included because it's a form data. And of course the body as well is there. Then there's a put example, and that's just some example I've got here, and it's just pretty standard as well. There'll be content length and the body included with that as well, sending data. And a delete is pretty straightforward too. It's just delete and what you're deleting, the file name, test.html, and just the host name. Web developers to know is absolute URLs, unless we use the full path, are not recommended since updates require editing of all requests based on location. So when you use absolute URLs, you're creating more work for yourself. You want to use relative URLs. So when you change, so you're not having to change everything. If you change your domain name, all you do is change the domain and the relative path should work. You don't want to have, it just gives you a bunch more editing when you use an absolute URL because they all have to be changed. It's easier just to have a relative path. The other just comment to make is that absolute URLs are only used when connecting to a proxy server, and that's the only time you typically sometimes use them. So response components, this is the other side of the coin. The response is from the server, so that's a status line, is the first thing, headers and body. So it's pretty straightforward too. HTTP method, post, put, and delete, post being the most common, protocol version, and status code. Then you got a variety of headers like server, date, content type. So some of these are common to both. Connection, whether it's to keep alive or not. Content length, content location, and set cookie. And the body, of course, the most important one, the HTML payload and informational messages that are included in there as well. So an example, post response, HTTP 1.1. And then a 200 is the OK, so the response code would be included there if it's HTTP 1.1. The server is Apache, and then there'd be a date timestamp in there as well. And content type is just basically whatever it is. Connection and content length 270, and the body and all the lines of the body, the data. And a put response would just be a 201 response code created. And there's the server and basically the content location where the put was and content length. And delete is just the same thing. It's just the delete response code 200K was deleted. Really nothing else to it. So what I'm going to do is I want to discuss the application deployment models. There's actually three of them altogether that web developers have to pick from. I'll start with the single server application deployment model. And the purpose of the model is to decide whether you're going to include all web servers on one physical server or break them up into separate servers. So to start with, I've got this single server, so that means there's one physical server, and you have your web server software, application server, and database all on the single server. And you can't do that. There's no problem at all. It's just based on the application size and sort of input and output you're going to require. The web server is the presentation layer, and that's part of just full stack architecture. It's the presentation layer. Then you've got the application server, and that's called the business layer. And that's defined with the web APIs and application logic. And then finally, you've got the database, and that's the data layer. And that is represented, of course, with just the database access and the database driver. And then you've got the user interface on the client here. So the advantages of this model, it's really designed specifically for intranet applications only. That's really where it's often deployed. You don't necessarily have to, but often it is because it's the scalability issues. It's low cost of deployment. You can put everything on a physical server. You minimize points of failure as well because you don't have connections between servers or switches. So low cost of deployment. There's really no network latency because it's all on the same server. The only latency you're going to have is between client and web server. No protocol chattiness involved since they're all on the same server, so you don't have any particular chattiness within the data center, although that's not really kind of a big problem anyway because the latency is so low. But it's not scalable. As the traffic grows, you're going to have to move that off to separate servers. You're going to have a lot of utilization or server processing delay. It could even be shared by other applications as well. You've got single security zone vulnerabilities that will show up because they're all on the same server. So if your web server is breached, it's going to leave the application and database servers vulnerable as well. And there's a single point of failure design because if you have any problems on the server, on any one server, and it's going to affect the other ones. This has more to do with hardware. If you have any hardware problems, it's going to affect all the servers you have. And of course, database server scalability issues is kind of an issue with this as well, since you can outgrow the single server model really, really fast. This is what's called a two-tier application deployment model. So at this point here, I've got the same web server, application server, and database server design. This time, though, I've moved the web server and application server onto a physical server and the database server onto its own server. And this is common because most of the traffic flow is going to be between application server and database server. There's going to be a lot there. And it's just the size of the database itself will grow often exponentially. And you just have to have that on its own server just for scalability reasons and performance, of course. So it's okay model for intranet and internet applications. It's a moderate cost of deployment. You can set up multi-zone server security, so that increases your security right there. Because you've got different servers and you can do filtering based on that. It eases up the server processing delay since now you're split off the database server. So your web server and application server will benefit from that. There's some what's called moderate level of reliability. It's scalable horizontally, so you can add horizontally. So there's some scalability there. Disadvantages, back-end network latency. There could be some if you have a lot of congestion on your back-end infrastructure. And that's basically it. There could be some protocol chattiness between application and physical server. But all in all, it will give you more scalability than the single server model. Finally, there's a three-tier application model, and this is probably the most popular because it's so scalable. You have a front end and a back end defined. And so it's the same servers now. They're all really on their own physical servers, so they're split up like that. So this is the most scalable. It costs the most to deploy, but you will get the most server security with this model because it's multi-zone. And it gives you kind of more of a distributed model as far as performance goes. You've got 3 different servers, so if you have problems with the one web server, you can add web servers quite easily to distribute that load. So that gives you that scalability that you really need for full stack applications. It's got the highest level of reliability. and really scalable as well. You can have horizontal scalability, adding database servers. So disadvantages, it's more expensive. You could get chattiness problems because you have the server split up now, so they have to do calls between each other on the server. So based on your infrastructure, you could have performance problems there. But otherwise, it's quite a good model and really good for security. Now, full stack web application dynamics. I'm just going to go through and just explain just the communication flow from client to server and how that works. So the client sends an HTTPS request that hits TCP 443 listener on the web server. That could be Apache, for example. It'll go and find the static files, and it's typically locally, HTML, CSS, JavaScript, images, fonts, anything that's static doesn't change. So we'll go out and do a request for those. That's locally, it's just locally stored. So it'll go out and fetch those. It'll pass that static HTML to an application server. And at that point, the application backend server reads the instructions in the web page and does a query to a SQL database. So here the SQL query is going to do some fetches. And what happens is the server returns a record set. This is dynamic content, of course, that's being part of the record set. And the record set from the backend database server sent to the application server and inserted in the web page. That's what the application server is doing. And then the application server forwards the HTML with static and dynamic content to the web browser. And basically, it just gets forwarded on back to the client, all the content needed to build a web page. The other thing to consider is the CORS header is part of that concept of you can't connect to different domains typically without permission. So CORS doesn't allow that if you have servers in different domains. So you actually have to allow that with a header to allow communication to a different domain. And CORS is part of that. So it requires you to set up the header and allow permissions for that to happen. And finally, I've just got some encoding methods here. JSON is really associated with APIs. XML and HTML are other examples. I just added them here just to show some comparison. They're all text-based. JSON is machine-to-machine typically, and that means server-to-server mostly. XML is the same, and HTML is client-server. JSON is fast, it's text-based, really fast. XML is a little slower, and so is HTML. JSON is not as secure. XML and HTML are actually more secure encoding methods, so that's something to be considered. JSON is just text and number based, whereas XML uses multiple data types, and so does HTML. JSON's based on, it's really basic, and that's what makes it so attractive, because it's just based on key values and arrays, whereas XML is a tree structure, and so is HTML. The character set encoding is pretty similar. JSON uses UTF-8 or ASCII, and so does XML. It also uses ISO, is supported. HTML supports ISO. So as mentioned, APIs are big with JSON, and XML and HTML. It's supported there as well, but JSON is primarily what's selected for APIs when it comes to data encoding. And that concludes HTTP fundamentals. Response caching order. So this is basically how caching works. Here on the left here, I've got a browser, and there's the origin server, or the web server, you can call it that. So it goes through 4 different stages here, or 4 different options. And if you're using a private cache, what will happen is, now I'm on the browser here. So if you're using a service worker, and that service worker programmatic caching method that's used in the local browser, and it's different from the normal HTTP cache. They're different caches, and they work differently. Service worker, if it's actually implemented on your browser, it's going to intercept that request first. And what it'll do is it'll return the cached response that you have based on the program cache strategy that's being used. Whatever's in the cache will be returned based on the service worker caching strategy. And if there's no service worker, then the local browser would be checked. That's just the browser standard local cache. And if the response is unexpired, the data is unexpired, then it just returns it to the browser, and the browser will use that. Just standard caching is what it is. Then number 3, if that's not available, it'll check the proxy cache or the CDN cache. That's called a delivery network like Cloudflare. It'll check that for a response and return to the browser unexpired. So if it's not locally, then the next thing is to go out to a proxy server if it's designed to do so, or a CDN cache. So it'll check locally first. The first 2 are local caches, and if not, it'll go to an external cache. And finally, if none of them are available, it'll send a request to the origin server for a fresh response if it has no valid responses, if they don't exist. So you kind of go through, you see the service worker intercepts the request and goes in and checks it's cached. Then the browser cache would be number 2 if there's nothing resulting from the service worker. Then then it would go to a shared cache, is what these are, proxy server or CDN. These are called shared caches. That's their architecture. And finally, that doesn't work. Number 4, then it's going to go off to the origin server and do a refresh. More information on caching. You have 4 types. You have private, public, no cache, and no store. 4 basic cache control methods. So to start with, cache control private has a max age. That's just the amount of time that it's going to be fresh in the considered fresh in the cache. It's a time limit. So the local browser caching only allows local browser caching when it's set to private. So it has to be local. And the max age is the time before it becomes stale. And the response authorization header cannot be cached locally. The next one is cache control no store, and it's got a max age as well. And this basically refers to reverse proxy and CDN managed caches. So here, you're not permitted to cache anything locally. That is saying you're going to have to go out to the proxy or CDN to check the cache there. So there's no local caching when there's no store. That's basically what it is. Then cache control public is anywhere at any time, really. You can cache it locally, intermediate proxies, or a CDN. So that's the most liberal caching policy available, is public. Then there's no cache, and that's the last one here. So basically with no cache, the cache is disabled and requires a response fetch from the origin server. And this is often things like very content-sensitive data or data that's frequently changed. And what happens, it requires that you send an e-tag with a value that gets compared on the server to determine if there's been any changes. So it's based on an e-tag value. And if it has been changed, the server determines it's been changed. The cache is outdated. It will update and just send the new value. There's also last modified with a date. That's just another way of doing it. That's sent to verify the currency of the data. So cache validation, response headers. So server sends an e-tag. It's basically what I'm saying. Server sends an e-tag when the resource is changed, indicating that, or last modified. And this validation is required to use stale data. So basically that's what it is. It's just a validation process that happens with that type of caching. Absolute URLs, I've kind of touched on this a little bit just to understand how this works or what it is. The difference between absolute and relative URLs. This is what you're probably more familiar with. It helps to know just how these things are, the different components. This is the different parts are shown here. Protocol is the first part, HTTPS, you know what that is. Then there's a subdomain, that would be blog, and the domain would be courses. And the top level domain would be .com, or it could be .org, .edu, whatever it is. Then in front of that, then you've got the path, that's web, and then the resource would be developer. And the same thing here, it's HTTPS, it's a protocol. The domain would be, there is no subdomain, this is just the high level domain, mywebapp.com, and there's the API path there. And here, this is done with the port, so it's basically the same kind of idea. The same protocol, subdomain, domain, and top-level domain. Only this time there's just a port number instead of a path. And here, this is localhost. This is done a lot for testing, for example. So you got a protocol, domain is localhost. So this is basically just locally to the server. That's all it is, just the local host. It's like a loopback. And there's the port number 8080. So what I'm going to do in this video is discuss DNS. DNS is a key protocol for any web application. So you really have to know a lot about how DNS works. So now what I'm going to do is with DNS and other protocols, I'm going to delve a lot more deeply into the specific network services within the application layer used by the application. And DNS is really a primary example of that. DNS lookup process. So what happens is the client will check the browser cache, then the operating system cache, then the router cache, then send a query to the ISP DNS resolver. So it does a bunch of local checks before it actually sends this DNS request off to the resolver. So if it's not locally, then it has to send it off. So it does. And the resolver will look in its DNS cache. If it's there, it will just return the A record and you're good to go. If it doesn't have that, say it timed out, for the TTL value timed out on the record, then the resolver has to do some things. So what it'll do, it'll send a request out to what's called the root server. And it'll say, what's the IP address of the top level domain server? So mywebapp.com arrives at the root server. It says, well, that's a .com. So for .com, you're going to need to send this to this TLD server. So the root server will send back the address of this TLD server. So there it goes. So so it sends this off. So this will give you the IP address of the authoritative service. So it's for the .com. This TLD is a .com top level domain server. And it will say, okay, this is .com. Now the MyWebApp part of it, you're going to find that in this authoritative server. So it goes back here, and then this sends this request off from the ISP resolver again. So the A-type record is actually at the authoritative server, and it knows what mywebapp.com is. So it'll actually send back the A record, this 200.2.11, to the resolver. It'll put in the DNS cache and send it back to the client. So basically, you go to root server first for the .com, and then you go to here. This is the top level domain. That's what our .com is for MyWebApp, and then it'll go back to here to the authoritative server for the full address and send back the A record. That's basically all there is to it. These are some DNS record types. You've got the top level A records, and these are just basically most of what you're going to get with DNS. So webapp.com is an A record, and there's the value, and the TTL is the amount of time it'll stay in the cache. Then you have C names, and this resolves an alias or subdomain to an A record. And these are less common. That'll be something like blog.webapp.com. So what'll happen is that'll get resolved to this web app, and that'll get resolved to an IP address. That's all it is. Then you've got MX records, and that resolves the host name of an email server for routing purposes as well. So you've got webapp.com as the host name, and what's its email server, mailserver.com. So that'll be returned, the IP address of that. So that's just mail servers. And then NS records are just the host name of the email server. So this is really the records of the authoritative servers, the name servers themselves. And that just, for webapp.com, it might be something like ns1.server.com. And finally, there's the 4A records for IP6, and this is just the same thing. Web app just resolved an IP6 A record to that domain. And that's basically all there is to DNS records. Fully qualified domain names. That's something where you've got a host name, domain, and top level domain, and that's what these are here. So it really gives you all the host name, just not the domain, and it'll include the host name as well. So in this video, I'm going to discuss authentication methods. There's specifically 4 methods I'm going to discuss in this video: basic authentication, session cookie authentication, JSON web tokens, and open authorization version 2. So to start with, basic authentication is something that really not recommended when you're dealing with the internet. It's often okay for testing or for working within a private domain, but it's really not used as much anymore and should be used with caution. So what happens is you've got a client, a server, So the client connected and with TCP, and it has to do authentication. So what happens is it starts with a GET request for a web page. So it sends a GET for the index HTML file to the server. What will happen is the server is going to return a post response code 401. That means unauthorized. So the server is saying you're unauthorized until you provide the proper credentials. So that's all it is. It's a 401 response code, standard. So the server sends this security challenge for a username and password to the client. So the client returns an encoded user ID and password, and it uses base64 encoding. It doesn't use encryption, it's just encoding. And so it encodes the user ID and password credentials in an authorization header to the server. So you can see the authorization header's got basic there, and then the credentials are just sent, would be sent right after the keyword basic. So what happens is the server will check the user credentials, and if they're okay, it'll send post response code 200 to say it's okay. And then what would happen is each time the client sends any request to the server, it'll have to include that authorization header password with every request. So it's a little bit cumbersome. You consider that's got to keep sending the password with every request. That's how it's set up. As mentioned, this isn't encryption, it's just encoding. Then there's session cookie authentication. So in this case, session cookies are used, and they're quite common as well, particularly with e-commerce. So the client sends a GET request for the web page server, so it's at that point in the web browser process to load a web page. So it requests the index page. So the server gets that request, and it sends a login prompt for the username and password to the client. So the client returns the username and password for authentication. Server checks the client credentials, and if it's okay, it'll generate a cookie with a session ID, and that's then returned in the set cookie header as a response back to the client. The client sends a request with the cookie that has the session ID for authentication. So each time it's sending a request, it's having to send that with it for authentication. The server checks the session ID with local session database on the server for all requests. So it's having to verify it with a local database that it maintains on the server. So that'll take up some space as well, and it'll affect the server processing utilization as well. But it is stateful. Session cookies are stateful, so it can match the client with the server and follow that state right throughout the browser session. So it works well for things like e-commerce. Then this is JSON Web Tokens. And this really applies mostly to APIs. So if you're doing a lot of APIs, JSON Web Tokens are a really good choice. So what happens is you've got the client here. Now he's going to start communicating with a JSON Web Token authorization server. So the client sends a POST request, this time with username and password. So it's not sending a GET, it's actually sending a POST request. And this is quite common with APIs. It's sending data to the server initially with a username and password without being asked for it. So it sends that to the JSON Web Token authorization server. The JWT authentication server verifies the user credentials and issues an encrypted session token. The client sends all subsequent requests with the JSON Web Token in the authorization header. So you can see here it's actually called bearer now. It's not basic. It's the authorization uses bearer, and the JWT token is sent with it in the request. And the server authorizes the token from the client and sends the POST response from the API if there's no issue with the token. And finally here I've got open authorization, or something called OAuth 2. And this is quite popular and used a lot. You can use it with APIs or really any sort of web-based transactions. So what happens is that you've got a client, you've got what's called a resource server, that's webapp.com. You've got an authorization server at the back here, auth.server.com. So the browser will send an authorization request to the resource server, webapp.com. It's an authorization request. The web server will redirect that token request to the authorization server. The bearer token is generated from the authorization server and forwarded back to the client. So the client now has the bearer token it's looking for. So that client sends that bearer token in the authorization header to the web server with each request. So that's basically how that's set up. It's quite easy. The web server checks the token, sends the post response with 200 OK status to client, and if there's any problem with it, it'll send a 401 unauthorized to client if the token's invalid. And that's basically how open authorization works. None of these give you encryption, and encryption has to be provided by TLS. The other thing to keep in mind is that session cookies, this disadvantage is that you need to have to set up a database, session database for that. So that's just another consideration if you want to set that up on your web server or go with another kind of option. Now, in this video, I'm going to discuss TLS characteristics. So TLS is the newest protocol that basically supersedes SSL. SSL had a lot of security vulnerabilities, and it was basically deprecated a while ago. Then TLS has been developed in place of it. There's 3 different versions of it, version 1.1, 1.2, and 1.3. Most of the implementations today are focused on 1.2 and 1.3. 1.3 is the most current version, and basically the difference between them has to do with just security and performance upgrades. So you're going to get a lot better security with 1.3, as well as performance characteristics as well. I'm going to discuss some of these things in this video. So this is a key topic for web developers, along with, like I said, DNS and firewalls seem to be really key topics to have a better understanding. So what I've got here is a TCP model drawing, and it's showing basically 2 options, either HTTP or HTTPS. And here the HTTPS refers to the usage of TLS as the encryption of data. And TLS is an application layer protocol, so it actually exists within the application layer, but it is underneath HTTPS when it comes to the actual operation and call of encryption from the application itself, from the web browser. And TCP 443 is well known. That's the it's TCP based, so it uses 443 as the application port. Then below that, you've just got the standard stack of IP, Ethernet, and physical layer. So currently, TLS is implemented on 80% of all websites. It counts for around probably 90-some% of all actual traffic. So it's mostly, and it's a blend of 1.2 and 1.3. 1.3 is going to be the main player, I'd say, next couple of years. It's got better features and all. So it's a client-server application, kind of what's called a sub-protocol in the application layer. And it provides 3 different services. The primary one and the most well-known is called in-transit encryption of header and payload. So it'll actually encrypt all the header and payload. So when it goes through the firewall won't see the contents as it transits the firewall. So that's important to keep in mind as well. So in transit, of course, is anything that's in transit between client and server. The other thing it does is it provides authentication. And that's important as well, and that's done with a CA signed certificate. So what will happen is the server will send its certificate to the client and it will authenticate it. And that's basically just authenticating the server, or the client authenticating the server and saying, yeah, you are the server, and it's okay to send data to you. So it's really authentication of the server itself by the client. And the third service is called data integrity check. And this is done with the hashing protocol. Usually it's SHA or HMAC. And so what this does is this makes sure that any payload that arrives hasn't been tampered with. It's been uncorrupted. It hasn't been changed in transit. So that's another key aspect as well that TLS provides. And as mentioned, it's got a socket listener on 443 on the server. And the client, of course, would just open up a ephemeral port on the client side. This is all really part of an HTTPS connection. So it's just TLS as a sub-protocol, so it doesn't have its own. It uses 443, so it's all part of the integration with HTTP. And as mentioned, TLS 1.3, as you're going to note, will have the fastest handshakes and strongest ciphers. Ciphers are encryption protocols. So here to start with, the server connection protocol. So anytime you start a browser session, you're always going to have the big three here, and that's DNS, TCP, and TLS. TLS is the third part of this puzzle. DNS, of course, we've discussed that, and that just resolves host names to an IP address. So DNS is always the starter protocol. And once that's done, then you'll get a TCP handshake, a three-way handshake. And the TCP starts, origin server will accept the connection from the client. And once that happens, then you go on to a TLS connection. And that happens right after TCP. And that's really negotiation of the TLS tunnel between client and server. So those are three, and that's the order in which they occur. Looking a little closer at the TLS session connection, like I said, there are three main services: in-transit encryption, server authentication by the client, and data integrity check in both directions, actually. So the client initiates the TLS handshake with an origin web server after the DNS query has been done, and the TCP handshake has happened as well. So the web server listener on TCP 443 is listening for inbound connections from the client. So the web server then will send a CA certificate to the client with a unique public key that's signed. And so that's really just to do the authentication piece of this process. The client will verify the validity of the certificate with the local store that it's got. It's just a browser. It's just a local store of CA certificates that's integrated with the browser just to verify that the certificate is valid from the certificate authority to authenticate the web server. Then the client creates a private session key from the public key of the certificate to create to provide encryption and decryption. That's called the session key, private session key. And just one other note: the TLS certificates are issued from a trusted public certificate authority, and they expire after 397 days. So that's one key aspect to keep in mind. Is often it's easy to forget that they will expire, and when they do, you're going to have a connection that's not going to work. So it's important to keep in mind that expiry date and to make a note of it, because it's often a kind of a problem that occurs for developers. Here I've got a TLS handshake, and this is more a general handshake of the kind of things that happen. The order in which this happens, or the different things, changes a little bit based on the TLS version. But basically, it starts from the client, and the client sends a hello message to the server, and it sends the TLS version it's using and the cipher support. Cipher meaning the encryption algorithms that it supports, like AES, for example. And the server will then send a hello message with a TLS certificate and a cipher agreement, saying it agrees on what cipher it's will use with the client, something that they both support. They have to both support and agree on a cipher protocol. So the client authenticates the server identity with the TLS certificate, and does that, like I said, based on the local CA store certificate that's integrated with Windows, for example. So the client and server will generate a session encryption key. It's symmetric. It means they both have the same key. And once they do that, the client will send a finish message to the server encrypted with a session key, and the server sends the finish message to the client encrypted with a session key. So they both have the session key, they know what it is, and they can encrypt, decrypt the data. HTTP strict transport security. And this ensures that any connection where this is enabled uses an HTTPS connection. Anything that's not will not be permitted. So it's a server-side security feature that prevents non-TLS client connections. The server sends the HTTP response header. It's called strict transport security to the client browser. And the client upgrades the URL to HTTPS, and if not, the server will drop the client connection if TLS is not supported. So it makes the client browser do an upgrade to HTTPS before the server connection is permitted. Things like this HTST, is recommended because it prevents man-in-the-middle attacks, cookie hijacking, and things like invalid certificate bypass. So it's just really enforces this idea of requiring a TLS connection to the server. That's all it is. I've got a couple of examples here, Nginx configuration. And you can see there's just it's got syntax for it, add header, strict transport security, and then a max age for it. And Apache would use header always set strict transport security and with a max age as well. So that's how you just enable that on the server side. That's you just put those commands in, and that will enable that feature. This video, I'm going to do an introduction to REST API application flow. I thought this was important to include with the course since REST APIs are becoming so prevalent, really important to web developers. So to start with, I've got a topology drawing here, and it just shows the application flow from client to right through a database server. So REST API is an architecture framework, and it's based on 5 requirements that are needed to basically be followed to call it a REST API. The first one is client-server architecture, and that's really in line with web-based applications where you have a client or browser and you have one or more servers. And so it starts out with the client making a request for some service from some data, and the servers doing the processing and returning the results. It also has to be stateless as well, just like HTTP. So it doesn't maintain any state information on the servers. You can on the client side, but not on the server side. That's another characteristic of it. The third one is uniform interface. And this is important that anytime you have a what's called a UI or a URL, it has to be unique to the API. And that's supported with get, post, put, and delete methods found within all web-based applications. The fourth one is that cacheable responses should be locally or done on a proxy. So they have to be cacheable, and you can keep them on the client locally or on some reverse proxy server. And the fifth one is a layered system end-to-end. And that really is based on what I've got here, this drawing, where I've got a client and multiple servers. So you should be able to support multiple servers with your REST API as well. There's no real limit on them, but it really is, it can get quite complex, but it has to be layered, starting with a front-end server and then back-end servers. So what I've got here is just an example of a client browser, and the client wants to connect to a weather network for, say, a 7-day forecast. So it starts out with a web API on the client that's going to communicate with API software on the Apache web server. So what happens is the GET is sent out with some particular standard relative URL, like API v2 weather daily, and then the version. So that's just a standard GET. But you also have an API key is sent with it as well. So the API key just authenticates the with the server for some sort of authentication that the session is permitted to take place. So then the GET is sent, and this is all after DNS, TCP, and TLS has set up the network connection side. So the browser initiates the GET request for some forecast data from the database server. The web server sends an API request to the backend API on the application server. So you can see that there. That's number 3 here, the API request. There's a variety of different encoding. You can use HTML, JSON, XML, or Python, but typically JSON is the most popular. So that's sent to the application server. Then the REST API there sends a query to the database server API software interface, and from there the dynamic content is then from the fetch is just returned back to the application server, where then we'll insert that into the HTML page along with the static content and return that back to the web server. So once that's there, it then gets sent on to the client. That's really all there is to it. The paths are sometimes a little different with APIs as well. You see a lot of conventions starting with api.weather.com, for example, then some query path attached to it. This is really basically an overview of it. It really is a lot of it's machine-to-machine communications that you would expect with an API. Then, of course, the connectivity and data returned back to the client. And that just kind of gives you an overview of REST APIs. So the final video in this HTTP operations section is called Web Transport API. So I'm going to discuss what Web Transport is and really how it distinguishes itself from web sockets. And it really is a replacement for web sockets. It's still in the standardization stage. As of 2023, it's just at that point where it's starting to be used. So I'd say by 2024, it'll be at a point where it's starting to be used. Developers will figure out how to program with it to replace WebSockets. So I've got the TCP model here, and I'm showing HTTP over TCP/80, HTTPS over TLS. These are all common protocols you know of. Then Web Transport, it's an API, so it's not a replacement for HTTPS, but it is for WebSockets. And it runs over TLS 1.3. So that's what you need for Web Transport. The other interesting thing, and part of what makes it so attractive, is it's integrated with QUIC and UDP 443. So this is really an HTTP3 compatible protocol, and it's designed to leverage the same sorts of advantages of QUIC that HTTP3 does, and that's from the perspective of performance and security. First thing is multiplexing low latency real-time bidirectional QUIC stream. So what happens is with WebSockets, you've only got a single TCP connection. With Web Transport, you actually have multiple streams within a connection. It provides just streams. Streams can be dedicated to reliable transmission as well as unreliable. So you can use both. It's really, really versatile. So it'll actually multiplex the low latency real-time data. It's actually a lot faster than WebSockets. It'll carry multiple voice data and video streams for the same and different applications. With WebSockets, the problem is if you're going to send different types of data, often it'll have to open up more than one connection to do that because it can't distinguish between the different data types. So often what will happen with WebSockets, you end up having to open up multiple separate connections. Whereas with Web Transport, you don't. It'll just open up another UDP stream, and that's all there is to it. It has that head-of-line blocking eliminated at the application layer. There is still some head-of-line blocking per stream, but it's quite insignificant. So you've got really all the advantages of that quick handshake. It's fast to start up, and it's really well suited to multiplayer gaming, live streaming, IoT, and machine learning. If you go in the Chrome testing section, there's an experimental QUIC enable right in there. So this is just kind of an overview Web Transport versus WebSocket. So Web Transport really is an HTTP3 connection. Now the problem with WebSocket is it's not really so much a problem. It's really an upgrade. You do have to upgrade from 1.1 to WebSockets with WebSocket. Whereas Web Transport, you don't have to do that. There is no upgrade. It just natively will support HTTP 2 or 3. So it's really designed for those faster HTTP protocols. And UDP 443 is what Web Transport will use since it's part of QUIC. It's UDP based, so it's a lot faster than TCP. Multiple bidirectional streams, whereas this is only a single bidirectional stream. You can send reliable and unreliable connections, so you can send things like data, voice, video, and some of them are unreliable. You can use UDP with voice and video, whereas reliable stuff like communications, you need TCP. So not TCP, but you can get advantages of QUIC to send reliable and unreliable connections because it'll support both. And they're both full duplex. Web Transport has no head-of-line blocking except for within a specific stream. It will fall back to HTTP 2, whereas WebSocket won't. Reverse proxy caching is supported on Web Transport, whereas WebSocket it's supported with WebSocket to some extent, but it's quite difficult. You do have to set up. You have to make sure you're using TLS, and there's some other settings, so it's not something that's natively supported. You do have to configure it. There's native core support with WebSocket. You actually have that too, but it's not native. HTTP authentication is available with Web Transport, And with WebSocket, it's custom authentication, so you really have to do some additional configuration. And you get really ultra low latency speeds with web transport that are possible over multiple streams. And WebSocket could be designed or could be considered as low latency. So overall, the web transport is a replacement for WebSocket, particularly for a lot of the applications that I've mentioned. Here is just an example, web transport example. So here, this is just making some connection. WT is just web transport. That's what's used there. And you've got an async function here to start the URL and initialize the transport connection. So you've got a new transport, and basically you've got another one, async function close transport. This is just basically the setup. And just basically some other, this is all JSON too, actually. So that just gives you another example as well of just some of the kind of initial setup for web transport. So there's a lot of additional really good documentation there to take a look at, give you examples of how to set this up. In this video, I'm going to give you an overview of Secure File Transfer Protocol. So you can tell by the name it's something to do with FTP. The previous FTP, or I should say original FTP, has been around for decades. It's an older protocol. It's well used. It works quite well. It's a little slower because it's a TCP based and there's a lot of flow control. The other problem with FTP is it's all clear text, so there's no encryption whatsoever. So currently, Secure File Transfer Protocol was developed to deal with that problem of not having any data encryption. So SFTP is FTP with encryption, and the encryption is based on SSH to do the data encryption. And the actual cipher is AES, and this provides this in-transit encryption of data between client and server. Now the other thing with SFTP is it's client-server only. You can't use it for server-to-server file transfer. It's just not supported. If you want to do server-to-server file transfer, you have to use something called FTP Secure. And it's a competing protocol to SFTP. So it's really just client-server only. So the server authenticates the client by either a username and password, and that's a part of SSH architecture, or you could use SSH private keys. So you have both options to do the authentication piece. The SSH private key is stored on the client and the public key is stored on the server. It's firewall friendly. It's a single connection for data and control channels via TCP port 22. I say it's firewall friendly because TCP port 22 is often already open on the firewall, so it just makes it easier to implement. It's got a lot of feature-rich file management capabilities on the remote server, and it's also complying with industry regulatory requirements like GDPR, HIPAA, and PCI. So it's really something the web developers need to become more acquainted with, since there is compliance with these regulations that's going to be part of your application based on what the application is. We look at our network communication stack. SFTP is an application layer protocol, and it calls TCP/22. So it's just basically built on an SSH session that listens on TCP/22 on the remote server. So this is kind of an overview here of how it works. You can see there's a client here, and a router to router and server. So going across an internet connection here, the client and the server, like you see there's AES there running on both. The server's listening on TCP/22. So what happens is, to start this session or really build this encrypted tunnel via SSH, what happens is the client and the server verify their identity. It's called mutual authentication. It's done via public key. So that means that the client will send a public key locally to the server. The server will also send a public key to the client. And this is done to authenticate identity only. So what happens is the client and server generate a symmetric encryption session key. And this is used for the encryption itself, actually. And finally, the server verifies the client identity via a private key stored on the client. What happens is FTP client starts the SFTP interface software. Client opens SFTP session via 22. So once you've done the public authentication between them, and you've used the public key to generate a private session key for the encryption tunnel, that's basically all there is to it. Then you can start the session. So this is basically the SSH part of it. Really provides this key authentication as well as the encryption part of it. Kind of useful to kind of use as a reference so you know the difference between them all. Secure FTP is what I've been discussing. FTP Secure is competing protocol or another option. And then there's HTTPS. So the architecture, this is just client server only, as mentioned. You can't do server to server. With FTP Secure, you actually can do all three. You can do client server, machine to machine, and it provides stateful connectivity. HTTP is stateless, it's a protocol, and will only do client server transfers. So the encryption here, SSH use AES, and that's just called an encryption cipher. It's quite good. SSL TLS is used by FTP Secure. So this really does encryption based on TLS. And TLS will use AES. And HTTPS is also TLS. So really the difference there is the secure FTP will use SSH for its encryption facility. As far as authentication goes, you can use username and password or public-private keys. You can use either one. You don't have to use keys, and it'll work just fine, doing that as well. And with FTP Secure, you have the same options basically, although the public key uses a certificate instead of keys. So we use actually something a little bit different. And HTTPS, and this is certificate because it's actually based on TLS, that uses a certificate for authentication. So that's kind of a small difference there as well. As far as the ports go, this is based on the fact that SSH uses TCP/22, while this one will just use 20 and 20 on the older FTP ports. And HTTPS will use 443, of course, because that's what TLS uses. This one will actually just still use 20 and 21. File management, there is that feature available. You can, in other words, you can manage directories and such with Secure FTP. With FTP Secure, you can't, or HTTPS. So you don't have that application layer feature available to do file management, and that's kind of important as well. As far as a channel goes, this is a single channel. That makes it quite effective and fast, whereas this is based on the old FTP model of a control and data channel, and HTTPS is on just a single stream as well. FTP compatibility, it's fully compatible. Here with FTP Secure, SSL, meaning the old SSL is not supported on some FTP servers. So that means TLS actually is what I'm referring to. But it's some FTP servers won't support TLS, so you'll run into a problem there because this is based on TLS. That's the only problem there. HTTPS, then you've got it's based on APIs and curl. So that's basically what you're going to be using there to do the transfers. Somewhat not applicable. Firewall friendly, yep. Here, FTP Secure is not. You probably have to get the firewall ports open for that one. And HTTPS is firewall friendly. Protocol standard, this is the current standard here, Secure FTP. This is actually deprecated at this point, FTP Secure. And HTTPS is quite current. Performance, it's moderate here. For large symmetric file transfers, it's moderate. This is quite fast, so it's probably the fastest actually. And best for download only is basically the only comment here. This is good for downloads, and you have browser timeouts. It's chatty, so you can run into some performance problems with that.